Alright, today we're going to do power functions, and then I need to define what a power function is, and one of the things that they talk about is this definition right here. They say, alright, again, a power function is right here. They give an example of this. Where k and a are non-zero constants. We have seen we saw power functions in Algebra 2. Look like this. We call them direct variations, or we called them inverse variations. This was the direct variation. It was kind of the equation of a line, but or a linear function that went through the origin. It didn't have a y-intercept. This one, I still have this backwards. I have this upside down, sorry. The other one, inverse variation, is where you have y equals k divided by x. Sorry, where x is in the denominator. And this looks like a rational function. And we talked about inverse variations when we were doing rational functions where you had x in the denominator. Both of these are power functions that where you have a constant of variation, and then you had a variable with a power. Now, what we're going to do in pre-calculus, the power is going to be something, or the a exponent is going to be something other than 1. In Algebra 2, when we talked about this a linear function with direct variation, the power of x was just 1. So it only crossed the x-axis one time. Well, and the second one was an inverse variation. If I rewrote this, it would have been k times x to the negative 1 power. And because it has a negative exponent, it graphed like a rational function, which was like this. So we did those in Algebra 2, but now we're going to talk about things that have their power functions, and then your a term is going to be it can be something other than 1. That's what we did, like what we just did in Algebra 2. So here they give some examples of power functions, and some of them are direct variations, and some are the inverse variations. The key component being is that all of these are monomials. It means it's just one term. Each of these terms has a constant, and each has a variable, and the variable has a power. So the first example that they give us is circumference, and the formula c equals 2 pi r. The power, what they're giving you is the power of the variable. In the equation for circumference, the variable is r. It's the dependent variable, which as the radius changes, the circumference changes. And then this power function is the power 1 and has a constant of variation is 2 pi. Okay, kind of simple. Same thing with the area of a circle. Area equals pi r squared. The constant is pi. It's just a number. It's a symbol, but it's a constant. It's a rational number. And the power of your variable is 2. So it's the power of this function is 2. All right, the next one is gravity. Is force equals k divided by d squared. In this problem, your k is your constant of variation, and your power is to the negative 2 power. Because if I rewrote this, and we write force equals k times d to the negative 2 power, because I can rewrite this function this way, so it has a negative exponent. And same thing with Boyle's law. Volume equals k times p to the negative 1 power. That's how they get the power as negative 1. Alright, so there's some examples. And then we talk about having some inverse or direct variation. Again, we did this in Algebra 2. Of these 4 examples above, which one would be direct variations and which ones are inverse variations? Again, how I remember it, an equation of a line is a direct variation. It's y equals kx. So if I'm multiplying my slope, or my constant, times x, which this is an equation of a line, just doesn't have a y-intercept, always goes to the origin. It's a monomial. but this is direct variation. An inverse variation is when you're dividing by your variable. So you're going to use some vocabularies and have to decipher how to write the equation. But right here, I need you to notice, it says, note, unless the word inverse is included, a variation statement, the variation is assumed to be direct. That means that you're going to multiply your constant times your variable. So hopefully with that, let's do some examples. The first example, they want us to write a power function formula. It says t varies as the square root of the pendulum's length. So they want us to write an equation as t equals, and it varies, just use the word, so that means I'm taking my constant, I'm going to use k, I can also use 1, varies as the square root of the pendulum length L, so I can take the square root of the length L. Another way of writing this, I can say k times L to the 1/2 power, if you want to take it to a power instead of using the word square root. Okay, because it says varies, I'm going to multiply my constant times the variable, and then whatever the power of that variable is, it should tell you in there. Alright, with example B, it says Q varies inversely as the square of P. So now this, because it has the word inverse, I'm going to divide my constant by my variable. So Q varies inversely as the square of P. So I'm going to take P and square it. Or I can write it as K times P to the -2 power. Okay, inverse means I'm going to take my constant and divide it by my variable. Right, in the last example, it says J varies as the cube of B. So J varies as the cube of B. Okay. Now let's see, that's just some vocabulary. Definitely interpreting the verbal description into an equation. Big concept that you're going to have to learn and do in pre-calculus that you use in calculus. Actually, one of those things you use in life. But okay, now one of the things that they want us to do is talk about how to graph these, and this is probably one of my favorite lessons to do, mostly because you follow a couple steps and you do a couple of them and they become rather easy, but you're going to be learn some steps how to graph these power functions without a calculator. And at first you think it's hard, but really it's not. So here it says the single term polynomial function is a power function, is also called a monomial function. Okay, I used those words a little while ago. They're monomials, and we're going to actually at some point learn how to graph them. Okay, before I go on, I want to kind of quickly review with you 4 functions that we did in Algebra 2. One of them was linear function, which I did in black, and if I was to graph this function, didn't really do a good job, but here, let's see if I can do a little bit better. Linear function. There's an equation of y equals 1x. So again, it's a direct variation. It has a slope of 1, and it goes to the point 1, 1. That's kind of an important piece right here. It goes here. Then the next equation that we did in Algebra 2, we did quadratic. It's going to look like this. Hopefully I can do a pretty good job. It's an equation of quadratic, y equals x squared. Then the next one we did the square root function, and it looks like it starts at the origin, and it goes up, and it goes to the point 1. Square root of 1 is 1. Kind of goes up like this. And then the next one we did is the rational function. In it, of course, looks like this. Inverse variation. Okay, all these, I guess this one should have gone more like this too. Okay, when we did these in Algebra 2, these were the parent functions for these. The linear parent function is y equals x. The parent quadratic is y equals x squared. The parent square root function is y equals the square root of x. And the parent rational function is 1 over x. Y equals 1 over x. Why we're pulling this back up here is all of these are power functions. But when we're starting to do this in Algebra 2, in pre-calculus, we're really just going to concentrate on just the first quadrant, because these are what I've given examples are our parent functions. Now we're going to have some different derivations of these monomial power functions, and they're going to be in either quadrant, depending on the characteristics. They're going to be in quadrant 1 and quadrant 2, or quadrant 1 and quadrant 3, right, quadrant 4. But what I've graphed here, what I kind of want to point out, all these parent functions, they've all gone through the point 1, 1. And why that's important is because it's when we're doing monomials, all of these parent functions, or these monomials, are going to go through the point 1k. That's very vital when we're graphing them. Now, again, let me talk about the power of each one of these functions, these parent functions. For the linear function, the power of x is 1. So anything that has when you're given a monomial or a power function that has the power of 1, it's going to mimic that of a line. If you're given a power function that has a power, or its exponent is going to be 2 or 3 or 4 or 12 or 13 or whatever, its right side of the graph is going to mimic that of the quadratic function. Okay? Now, if you're given the power function that has the power that's a fraction, that is less than 1. So let's talk about this. Where a is your power. Your a is your exponent. If it's greater than 1, it's going to mimic that of quadratic. If your power function is going to be, which is your a value, is less than 1, but greater than 0, it's kind of important, it's going to mimic this shape of the square root function. Alright, the last one is if you're given a power function that has its power that is less than 1, when a is less than 0, if that means it's negative, it's going to mimic that of the rational function. Okay? Now these numbers will change. Your powers will be -3, -5, negative whatever. If it's, no matter what it is, it's this piece on the right side in quadrant 1, it's going to mimic that of a rational function. Okay, I just want to interject that when we start talking about it. Alright, now on this page it talks about graphs of power functions. Kind of did a little review with you on what some of the graphs of power functions that we did, or parent functions that we did in Algebra 2, and just at least give you a starting spot. Okay, so suppose you're given a power function and you're told to graph it. Where would you begin? There are a few things to keep in mind when graphing f of x equals k times x to the a power. If a is positive, the function passes through 0, 0. That means it's going to go through the origin. Let me just say, if the power, your exponent is positive, if it's 1, 2, 3, 4, 5, 1/2, 1/3, 2/3, if it's positive, your graph will go through 0, 0. If it's negative, the function will be asymptotic. The reason it's going to be asymptotic is because it's going to look like the rational function we just talked about. So that means if your a value is -2, it's going to look, it's going to not go through 0, 0. It's going to be undefined there because it's going to, your x value or your variable will be in the denominator of your function. Okay, so let me just kind of talk about, I just did these same exact graphs a minute ago. What's in black is, this looks like when your power is 1. It looks like it's going to mimic that of a line. If a is greater than 2, so for instance, greater than 1, like 2, 3, 4, the right side of this graph looks like that. I mean, your power function is going to look like the right side that of a quadratic or cubic or whatever it is. It looks very similar to quadratic. If your a value is less than 1 but greater than 0, if it's a half, 2/3, 1/5, so if your power or your exponent is a fraction, it's going to look like that of the square root parent function. Okay, right here. And then again, the last example, which I think most people have a hard time with, is if a is less than 0. Right here, it's going to look like that of a rational function. Okay, now one of the things that here I need you all to realize is that all of these is if your a value, I'm sorry, not your a value, I'm going to erase that, is if your k value, I need to write here, if your k is positive. So if k is greater than 0, it's in quadrant 1. If you're given a power function and your k value is less than 0, it's in quadrant 4. Okay, that's what it says here in step number 2. Now, then the next step, what we have to do in order to graph this, is to decide whether it's an even, odd, or undefined function. So when we talked about even and odd functions, we needed to figure out whether if the cheat is if your power is an odd number, 1, 3, 5, 7, it is odd. It's going to reflect about the origin. If your power is even, 2, 4, 6, 8, it is going to reflect about the y-axis. So you have to graph both parts of the function. Where you start is, we'll walk through a process. You need to decide whether it's in quadrant 1 or in quadrant 3. Then you decide what it's going to look like. It's going to mimic that of a linear function, if it's going to mimic that of quadratic, square root, or linear, or rational, sorry. Then you're going to graph half of it, then decide whether it's even or odd, and draw the same exact graph that reflects about the origin or the y-axis. Okay? A lot of talking, see if I can go through an example of one. Okay? So the first example, what I'm going to do here, okay, is they have an example, is f of x equals 2x to the negative third power. So the first step is I'm going to decide which one this looks like. I'm given not very much time to graph, so I'm going to be patient with me. I might have to graph it on another piece of paper. So I'm going to rewrite this f of x. F of x equals 2x to the negative third power. Or f of x equals k times x to the a. This was our, like our blanket power function. So in example A, k is 2 and a is negative 3. Alright, so with that being said, I know that because my a value is less than 0, it's going to look like that of a rational function, okay, because it's going to be written in the denominator. I can rewrite this as 2 over x to the third power. If I did it this way, most of you all would realize, oh, okay, my x is in the denominator. This needs to be half of my graph needs to look like that of a rational function. Alright, so my k value, because it's 2, it's going to be, and it means it's positive, that my function is going to be in quadrant 1. Half of my function is going to be in quadrant 1. So quadrant 1. Okay. Alright, so I know that this graph is gonna go, I don't think I can do on this piece. I'm gonna graph this one right here. Alright, so I know, because my little pen is way too thick to get on that graph, but that's right, you can follow along. Alright, my graph is going to go, first off it's going to be in quadrant 1. My graph is going to go through the point 1k. So the point that this graph is going to go through is 1, 2, because my k value is 2. I'm going to change my color. I also know that it's going to mimic, it's going to be that of half of it. It's going to look like that of a rational function. Okay, now we got to decide whether this is even or odd function. If it's even, it's going to reflect about. I have to draw the other half across the y-axis. If it's odd, I need to reflect the other one about the origin. Okay, the big cheat on this one is my exponent is, or my power is an odd number. It can reflect over the origin. If I need to prove that it's even or odd, if you're asked to do this, I'm going to prove whether this function is even or odd. I have to substitute negative x in for my x value. I don't know why I changed the color. Hold on. Okay, so if I did this, if I'm going to substitute negative x into my original function, and then I'm going to get out 2 over negative x to the third, because negative x times negative x times negative x is negative x to the third. It stays negative. Because when I get this, when I substitute a negative x into my function and it comes out with the opposite sign of my function, this proves that this is an odd function. Because I just did that, what happens? I have to take this function, this half that I've already graphed, and reflect it about the origin. Okay, so here's my, so this right here is a graph of my entire function. Because I've run out of room, I'm sorry, I'm going to have to continue the next one somewhere else. But anyway, my function, let me see if I erase this, what it will graph like. Okay, so here's my, goes through the point 1, 2. It's going to look like that of a rational function. Because it's an odd function, it's going to reflect over here. So this is how you graph. And this is the point 1, 2. So this is what this graph looks like. Okay? I don't know why I'm making this look so ugly, but whatever. That's just one example of how to graph a power function. Okay? So I guess if I wanted to do it over here, it would look like this. I can't do it on that small little graph paper. Okay, let's see if I can't do the next one. Alright, how to do the next one. Now this created by Alan Parr, words, cracking me up because it's right in the middle of where I'm trying to graph. That's okay. Okay, so I want to, I'm going to write up here, I have a little bit more room. In letter B, my example B, my k value, k is negative 0.4, okay. Because it's negative, my k value is negative, that means that my graph, half of my power function is going to be in quadrant 3. Right, quadrant 4. Golly, I apologize. Negative 0.4. Crazy. Still not going to be able to graph that. I'm going to have to graph it over somewhere else. And my a value, or my power, is 1.5. Okay. Now, because my a value is 1.5, that means that it's greater than 1. So it's gonna look like right half of my graph is gonna look like that of a quadratic. All right, now let's see if I can't graph this. Make a little bit of room. Sorry, guys. Can't do that. All right, sorry. I'm going to graph this one over here. So it's going to go through the point. It's going to be in quadrant 4, so it's going to go through the point 1, negative 0.4. Let's just call that 1, negative 0.4. And then it's going to look like it upside down. It's half of its graph is going to look like that of the right side of a quadratic. Now we have to decide whether this is an even or odd function. Kind of a funny one. So when I was doing this problem, I was just a second ago, I said, oh, this is a funny one. The reason it's funny is because I was looking at my power function. Again, this is right here. This is when I'm graphing letter B. I was looking at my power. I graphed half of it. I know that it goes to the point 1, negative 0.4. I should have done that a little bit. Looks like it goes to 1, 4. Actually, it goes to the point 1, negative 0.4. And then I was thinking, okay, let me just look at it where I'm going to graph my other half. Do I graph my other half of this in quadrant? Am I going to is it going to be in quadrant 2 or 3? Is it going to reflect over the origin of the y-axis? I thought, okay, how I'm going to look at that? My cheat being I need to pay attention to my power. My power is 1.5. I don't know if that's even or odd. So okay, so should I plug in negative x, decide whether it's an even function or an odd function? And then I was like, okay, well, I don't know if it's negative x to the 1.5 power. What is that going to be? Then it dawned on me, it's neither. So because it's neither, I only have to graph. It's neither an odd function nor an even function. So I only have, because it's neither, I only have to graph that one portion of the function, and that's the right half, the right side of it. So for letter B, I'm done. Okay, even though it looks kind of weird, pretty much done with that one. Now the last one is letter C. I'm going to slide it over a little bit so I have a little bit more room to graph it. Okay, now the first thing I'm going to do on letter C is I'm going to decide that my K value is negative 1 and my A value, oh wow, again it is a fraction, or it's a weird one, 0.4. Okay, now because K is less than 1, that means it's going to go through it's going to be in quadrant 4, so it's going to go through the point 1, negative 1. Okay, and because A is less than 1, or i.e. it's a fraction, it's going to look like that of the square root function. So it's going to look like this. Okay. Now I got to decide whether this is an even function or odd function. And it's a decimal. It's kind of strange. I don't know how I'm going to do this. Another way I can write this is half of x equals negative 1 over x to the 1/4 power. All right, now. Just thought I made a mistake. Guys, 0.4 is not 1/4. It's stupid. Being silly. Need to erase it. Don't know if I can now. Nope. Okay, I'm going to start over again. Actually, 0.4 can be written as 2/5. And I still wrote this all wrong, so I need to scratch this f. It's f of x equals -1 times x to the 2/5 power. Made a commonly made mistake. Most people do, but needless to say, this, I graphed it right, I just had the wrong fraction. This is 2/5. Now I still got to decide whether this is an even or odd function. Again, this was weird, trying to figure out another way, an easy way of explaining this one, that it's not so hard, without having to reduce this radical. And this is one of those things that we did in Algebra 2 that we spent, if I rewrote this, this would be 5, and we spent some time about this one, but still think this is, it's going to be an even function, because if I plug in a negative x into this right here, if I substitute a negative x into this, I'm always going to square that negative, and it's going to become positive. So that means that I'm always going to get I'm not going to change the sign of my function, so it's an even function. It's not neither. This one's going to reflect over. I still did a bad job on that one, graphing it, but it's going to reflect over the y-axis because it's even. Then, just doing this problem made me dawn on how to rewrite in letter C. I could have rewritten letter C in this format. F of x equals -0.4, and then 3/2. Let's see, x, this would be 1.5. Okay, I could be written this. This is what letter C is. X to the 1.5. Okay, that was letter C. Again, I can rewrite this in this form. This 2 would be outside the radical, and then x cubed. Again, if I plugged in a negative x in for here and did this, if I was to proving whether it's even or odd or neither, I can't, if I plugged in a negative x, so let's just say -0.4 squared. If I did this, negative x into this function, I'd get a negative x times negative x times negative x would be negative x cubed, and then I can't take the square root of a negative number, so that's, again, I'm just proving why it's an odd, it's an either function. But I could do in letter C, I can prove that it was even or odd, because every time I square a negative, I get a positive number, so it proved that it was even for letter C. Okay, so it wasn't such neat examples, but when we do this, hopefully I'll have better graphs for you. Just quick little overview on graphing power functions.